looking at modeling and optimization. This is section 4.4. And we use calculus to model things and to optimize. This is really helpful if you're building something, and engineers use this a lot. And I'm going to give a very classic example is modeling the building of a box. Okay, so what we're going to do here is we're going to design a box. So let's imagine we work for a company and they've asked us to design a box, and it's a metal box. Okay, so here we go. And so we have this sheet of metal, and the metal's already cut. And this is the metal that we're going to work with. And we were asked, let's see, I can look in the book. Okay, 25, they use inches, which I'm not thrilled about. So it's 25, let's pretend it's centimeters. And then we have 20 centimeters. And let's imagine we work for a meteorological company, and we're building these boxes to catch rain, and because we want to measure how many inches of rain. And we want to be prepared for as much rain as possible, and this is the sheet of metal we have to actually build this box. So it's an open box, there's no cover, and so they've gone to their engineers and said, could you please design us a box that will have no cover? It's using this piece of steel, and we'll just weld it together. But we want it to hold the maximum volume. What dimensions must this box be? Now, what we're going to do here is we're going to need to cut out the corners of the box. Imagine we're going to cut out a corner here, and just so I'm going to copy this corner. Let me copy it, and I see if I can paste it. Probably what I should do is, let me see if I can. The corners that I'm cutting out are these perfect squares. Okay. So I'm going to cut a corner out of every corner of this box. I cut a square out. Okay, so let me put one more. And so if I cut a square out of this box, then what happens? We've lost the square, and we can crease the box where the blue is. So where you see blue, we're going to crease the box. And what we have is this is actually the base of the box. Right? Now, these squares, we've actually cut them out. They're not there. Okay? They've been removed, so I'm putting lines through so you can imagine that they have been removed. And we're going to fold up on the blue lines I just drew. So this is the back of the box. This would be the front of the box. It would fold up and be the front. And then, of course, we have a side here. And then we have a side here. And so when we're done, the box, you can just sort of imagine, I'm going to move the box over a little bit to the left. And so let's see, when we're done, imagine that the box, and here's a little small version of the box, but it's going to look, let's see, like this. This is the front of the box. Like that. And if I want to copy this whole thing, it's going to disappear for a minute, copy it, and I'm going to paste it back. So imagine that's the back of the box and the sides of the box. It would sit up like that. Of course, you actually couldn't see this. You couldn't really see that. All right, so here's our box. It looks something like that. And it's our rain catching box. Does that make sense? Okay. So let's think about the dimensions of this box. It's 20 centimeters long, right? But we have to actually remove a perfect square. We're going to cut a perfect square out, and the square is going to be of dimension x by x. Okay? So the actual front of the box, the length of the front, is going to be 25 minus 2x. Does that make sense? If the front of the box is right here, that's 25 minus 2x. There is x. And if the entire thing is 25 centimeters long, then clearly the front of the box is 25 minus 2x. Does that make sense? Mm-hmm. Okay. The side of the box Let me move the box over a little bit. I'll put it up here. The side of the box right here, this distance here, that's clearly going to be 20 minus 2x. Does that make sense? And then the height of the box, what's the height of the box? X, right? So what we want to do is we want to figure out what must x be to get the largest volume. So I'm actually going to move this up. It's going to disappear again for a minute because I'm getting short on space. Okay, so we want to know what's the volume of the box. Well, the formula for the volume of the box is length times width times height. And we've just come to the conclusion that the length, or let's say the length of the front of the box, is 25 minus 2x. The length, we're calling the length, is the front of the box. And then we have the side of the box, that could be our width, is 20 minus 2x. And then the height is h. I'm sorry, is x. H is x, right? So there's the volume of the box. So the volume of the box is a function of x, and we want to know when is the volume of the box the highest. Now before I start working on the calculus of that, I'd like to look at, volume is now a function and x is the input, it's the domain. Are there any domain restrictions? We've got to look at what are the domain restrictions for this. So domain restrictions would be, how is x restricted? Can anyone think of how it's restricted? How large can x be? You're close. You're right to think small, certainly smaller than 20, but even small, right, half of 20, right? Because just think about if first of all, it has to be greater than 0. X has to be greater than 0, because if x is equal to 0, we cut nothing out, we don't have a box, right? But if you think about it, if the box, let's imagine that we cut out the square and we actually let it be 10. Well, we come to the halfway point, and if we cut out 10, right? Imagine this is 10. This is our square. If it's 10, then our next square would also be 10. And we cut out a square here of 10. And we cut out a square here of 10, because 10 and 10 is 20, and all we end up with is a rectangle in the middle, so it can't be 10. It has to be less than 10. Does that make sense? All right, let me get rid of what I just did. Okay. So, there is a domain restriction. We have to be between 0 and 10. Okay? All right, so now let's go, I'm going to sort of zoom in on this volume. Let's take a look at this volume equation. Oh, I guess let me see, pull that back. I seem to have a shadow there. Let me pull in a little bit on it and see if I get the shadow. I still get a shadow. Okay, I won't pull in. Okay, I'm going to keep it out. I just don't want to lose it on the shadow. I seem to have a shadow in the video, and I don't want to do that. Okay. Now, I think the first thing I'm going to do is I'm going to factor out a negative from the first binomial just to clean it up. If I factor out a -1 from the first binomial, then that 25 minus 2x becomes a -25 plus 2x, or 2x minus 25. I just wanted to put the x in the front, make it a little neater, and get rid of the leading negative that I'd have on that. Do you follow what I'm saying? And I'm going to pull a -1 out of the next binomial, factor it out, which would make the next binomial 2x minus 20. And this is times x. So a negative times a negative is a positive, right? So these two cancel out, so that becomes positive, and that's positive, and I don't have to worry about them anymore. Now the next thing I'm going to do is I'm going to multiply 2x minus 25 times 2x minus 20. Well, 2x times 2x is 4x squared. I'll put this in parentheses. And then we have, let's see, 2x times a -20 is a -40, or 2 times a -20 is a -40, and 25 times 2 is a -50. So it looks like, is that right, -90x? That sound correct? And then a negative 25 times a negative 20 is a positive, what is that? 500, yeah. And this is times x. So we'll finish this off by distributing the x, and we get a cubic. It's 4x cubed minus 90x squared plus 500x. That's the volume of the box. Well, that's great. We now have the volume of the box. We want to know when is the volume of the box going to be the largest. And so, and we know there's a domain restriction that x can only go from 0 to 10. Does that polynomial look correct, you guys? Yeah? Okay. So let me go ahead and I'm going to grab the domain restrictions and I'm going to grab the function, and we're going to figure out, using extreme values, when the volume function is at its max height, because we want the largest volume, right? So I'm going to copy this, and I'm going to add a page below. And okay, all right, there's our domain restriction, and we move up our volume. So let's go ahead and take the derivative of this, right? What is the change in volume with respect to time? And this is just power rule because it's a simple smooth polynomial, right? So it's 12x squared minus 180x plus 500. Okay, that's a quadratic, right? And so we want to find critical points and endpoints. We're looking for extreme values. This is because we want to know when a thing's the highest what are our max and mins. So when we're finding extreme values, we want to check. What do we want to check? Two things. We want to check two things. 1, 2. What are they? That's critical points. You're very close. But extreme values occur at...
Oh, the
yes,
I.
right? Critical points and endpoints. Critical points and endpoints. So and we have endpoints. They occur at endpoints and at critical points. We have the endpoints. The endpoints are at x equals 0 and 10. So we've got to check those. The critical points, now this is what Lauren was just saying. The critical points occur when y prime, or I should say v prime, right? Because it's v. v prime equals 0, or v prime does not exist. Okay? We don't have to worry about does not exist because it's smooth and continuous, it's a polynomial. But we definitely, y prime equals 0, we're going to have critical points. So we need to find what is x equal to here when v prime is 0. We've got to go use some calculus to fill in that box, okay? There's no does not exist though, because it's a polynomial, it's smooth and continuous, okay? So our mission is to find the critical points. We just don't know what those are. We know just the endpoints, and we know there's no does not exist. So what I'm going to do is I'm going to take my derivative and set it equal to 0. Now, I certainly can reduce it, can't I? I mean, my derivative is 12x squared. This is a quadratic. For a higher degree, we might have to use synthetic division. We're going to be looking for its roots, right? Oh, I actually made a mistake, didn't I? I'm sorry. Say that again, Stephen? Oh, that was a mistake you pointed out. Yeah. Okay. How about we reduce this? We could divide this by 2, making it 6, 90, and 250. Is that okay? Right? We cut this. This can be 6x squared minus 90x plus 250. Now, before we jump in here and factor this quadratic to find the roots, If you're on the AP, taking the AP exam and it's a calculator section, I suggest you use the quadratic program in your calculator, putting in A, B, and C and finding the roots. You should all have that. So pull your calculators out and tell me. Putting in,
I don't have that.
you don't have it? You should have that. Putting in 6, negative 90, and 250, what are the roots? Because I know you know how to factor, that's not a problem, but if we're taking the AP exam, and this is a calculator section, we're not going to waste time factoring. We are simply going to go to Program, and you should, in your calculator, if you don't, I'm going to give it to you, have the quadratic program, and you put in 6, type in 6, negative 90, and 250, and it'll give you the roots, and it's, in this one, the roots are irrational. So another way to find it would be the quadratic formula, okay? But you all know the quadratic formula, right? Negative b plus or minus the square root of b squared minus 4ac over 2a. I know you have it all memorized. So we don't really need to use that. We can just use our calculator. And I get x is equal to 11.3.
Last call for freshmen for reconciliation, and would sophomores please come down outside the chapel at this time?
And
Sophomores who would like
3.68.
to go to confession.
There we go. Okay, there we have them, right? I just put them in, and I'll give you that function if you don't have it, the program, quadratic program. All right, so now we're going to find out what is the volume at 11.3 and 3.68. Again, you can put this into your calculator. Oh, this is so true. We have a domain restriction, don't we? Yeah. We can't forget our domain restriction. So actually, let me put a little 11.3 is outside of our restriction. So we're just going to test 0, 10, and 3.68. So we want to know, what is the volume when x is 0? What is the volume when x is 10? And what is the volume when x is 3.68? Because these are going to give us extreme values. The volume when x is 0 is 0, so that's too small, right? The volume when x is, oh yes, it is. Thank you. It's 250, and this was centimeters, right? It's because if x is 0. Oh no, it's not. You're looking at the derivative, so it is x is 0. Okay.
Oh, sorry.
Stephen's right. Yeah. Here, look, we're looking at this function right here. Yeah. All right, and we want to, so that's what we're looking at. So when we're defining our volume, don't forget that we're actually looking at the volume function. Take down here, okay. So when x is 0, so did someone plug into their calculators, what is it when it's 10? 4 times 10 cubed minus 9. Do you guys have calculators? So Maya, can you give me v of 10? And Katie, can you give me v of 3.68? I'm going to figure out. So this is clearly we've got a min. I'm guessing this is a min. I don't know that it's a min. I could be wrong. I'm guessing that this one's a min. We could have a negative. Well, we wouldn't have a negative volume, would we? We wouldn't. We can't because we've taken care of that with a domain restriction. Maya, did you get v of 10?
Yeah, it's 0.
What?
It's 0.
Oh, it's 0. Okay. Okay, and what's v of 3.68?
820.
820 and a half. I should, that's right, these are centimeters cubed, right? These are all centimeters cubed. And it probably, yeah, if you, okay, then this is centimeters cubed. And this is centimeters cubed. And I probably, if I write this, let me move it at 10. 10 occurs after 3.68. I should put these in order. So it goes from 0 up to 820.5 centimeters cubed, and then the volume decreases back down to 0. So clearly, that's a max volume. So the max volume occurs at x equals 3.68, and it's going to be 820.5 centimeters cubed. So if we go back to our previous problem, or the previous slide, same problem, we found our max. And that is when we cut out these squares, they're going to be 3.68 by 3.68, and we'll have the largest volume for this box over here. And that's an example of an optimization problem.